my name's John. For those who I haven't met before, I am on our AI Growth Eng team. So doing a lot of our kind of go-to-market technical materials and meetups and events and things like that as we go through, and then get to work on some of our more exploratory research projects as well. Today we've got kind of a slightly different structure for the meetup or for the paper reading. So we're actually going to start with a little bit of like a couple industry news recap items, just a couple of things that have been released in the past couple weeks or so that we thought would be interesting to highlight for one reason or another. There's way more that got released that we're not going to cover there. So this is more just like us cherry picking a few stories, a few models that are interesting. And then we're also going to talk through, for the meat of the time, we'll talk through a paper as we normally do. We've got a paper today called Merge, Ensemble, Cooperate. Has a longer title, but essentially the paper is a survey of how you can, of different strategies and techniques for models to collaborate. And so we're going to look through that, talk through that, and talk a little bit about how that relates to some of what we've done for previous sessions and meetups and material that we put out around multi-agent flows and agent flows. So we're going to kind of make that connection as well too as we go through. But with that, let's jump into the industry news recap items. Again, we've kind of just cherry picked a couple things here that I personally think are interesting for a couple different reasons, and we'll go through those in a little bit of detail. So the first one of those is OLMo 2. And before I actually jump in, one last thing. As always, if you have questions, if you have thoughts throughout, feel free to drop them into the chat as we go. It's always more fun when people are kind of asking questions. We can jump into other topics as we keep going through. But yeah, with that, let me start with the OLMo 2 side of things. So this is a new model that got released, I believe it was the 26th of November. We'll talk about the performance in a second. I'm actually going to jump ahead one more page here. But yeah, so it was released the 26th of November. It is from a company called Allen AI. And one of the reasons this is a sort of notable thing that we wanted to raise is they have gone very, very much all in on this open ecosystem, open source kind of mentality, where they've released not just the model weights, but they've released the data behind that was used to train the model. They released the code that was used to do it, the intermediate checkpoints, and then the models themselves that have been tuned in various different ways. So they've released about as much as you can on how this model was made, what it looks like, and how it is working there. Couple different variants that they've put forward, but they've basically been able to achieve, if we look back at some of the performance here, they've been able to achieve like similar to a Llama 3.1 level of performance on at least English data sets. I think they specifically talk about English language data. But they've been able to achieve a decently high performance mark while also just completely open sourcing the whole of everything that they did, which is kind of a cool thing. You can actually see everything that they did to create the model, or the two models in this case. And you're not just looking at kind of any model that was created, but like one that was actually pretty performant as you go through. So they did this through a couple different techniques, and there's a bunch more information on their site if you want to dive into details here. But just a couple things to call out of how they were able to achieve this kind of performance. One was trying to focus a lot on stabilizing training runs. So if you're going through training runs, sometimes you can have these spikes of like loss ratios or things like that as you start to get instability in your training runs. They focused a lot on stabilizing those longer training runs to avoid those kinds of spikes. And then they used a couple techniques to essentially like patch models late in the pre-training phase. So they were finding that there was models that were missing some information that they needed. They were missing some kind of certain subject matter areas. And so they used a couple techniques. Basically, like they took the learning rate and annealed it down to zero over time, along with kind of using this curated data curriculum to essentially like patch the models as they get late in their pre-training phase, which is kind of an interesting technique there. And then the final thing I'll call out is that they also preset their evaluation metrics. So basically, what are they using to figure out if the model is performing better over time, or better throughout the training process, basically? What do they use to guide their training? Like, what's their North Star? They preset that ahead of time. They actually created their own set of benchmarks there. And there's an interesting bit of their announcement as well, too, where they talk about how they believe that companies who are putting out open source models should also put out what is their North Star, like what is the sort of metric that they're using to guide their training. And so they released the one that they used here, and then kind of, again, put that forward as something that they want to have other companies do in the future from the open side. So why do we call this one out? I think it's notable to me in a couple different ways. One is this distinction of really, really open in how they've developed the model. So they make this distinction of open weights versus partially open versus fully open models. It's a little, I think it makes sense from them to do because it's a way to differentiate what they've done, but it also is an interesting thing because if we see more model companies doing that over time, it just means more available information around how model training is being improved over time. So it's kind of a hopefully the start of a trend there, but we'll see if that actually gets picked up by other companies. And then the other piece is that they use this Pareto frontier metric that I think is also kind of a clever way of doing it, of looking at essentially the training, the flops used in training, basically, and then the performance of the model across different benchmarks. And so they come up with this idea of the frontier of where a lot of models are for that. It's a little bit fitted to exactly the performance of the model, so I don't think it's quite like a mathematical frontier, but it is an interesting way of communicating the performance of a model relative to the training that it went through. And then the other one to highlight briefly before we jump into the paper reading is another model that came out, again, similar kind of time frame on 28th here was the announcement. And the model is called QwQ 32-bit or 32 billion, excuse me, preview. I think the way you're supposed to say this is huge, but that sounds completely off to me. So I'm going to go with QwQ as we talk through this. But essentially this was, it stands for Qwen with questions. So it's a variant of the Qwen model. And really the main reason that this one is interesting to call out is because one, it's a high performant model on certain kinds of tasks. And those tasks align a lot with what we saw from OpenAI's O1 model. So for those who joined us for the paper reading for O1, or those who've just been following the O1 side of things from OpenAI, it's a model that excels at mathematical analytical reasoning, and it uses a sort of chain of thought approach almost to improve its ability on analytical fronts. But it's not quite as good as other models on more nuanced language or some other kinds of like language-based reasoning. And so when that came out a few weeks ago, we actually had a paper reading and we were talking about, I wonder if this is going to be a new kind of model that people try to create. Is this more analytical, logical focused one? And so this is just an example of some of that actually happening, where we're seeing a more analytical focused model. They kind of use a similar chain of thought approach. And so it's kind of we're seeing that potential trend happening now. We're seeing models that are more focused towards that analytical, logical reasoning by using that chain of thought approach. So kind of an interesting thing to seeing that come through. And then anecdotally as well too, QwQ's been very popular on your sort of open source communities, your Discords and your Reddits and things like that. We've seen a lot of popularity from that as we go. So that's been an interesting one to see. And so I think another one we wanted to highlight just because it's kind of indicative of this trend of this chain of thought approach used towards other kinds of models. Awesome. And so with that, we'll jump into the paper reading from here. One kind of question as we go into that too, I think we'll drop like a little bit of a poll in the channel. Want to see if you guys like this approach where we cover a couple industry updates and things like that, or if you'd rather just have us spend the full time diving into a paper in detail, because we kind of wanted to see which one is the preferred approach there. So if you guys don't mind dropping a response to that there, that would be great. And with that, we can keep going into the paper reading section where we'll spend the rest of the time today. So the paper that we have today is called Merge, Ensemble, and Cooperate. And again, it's a survey of different collaboration strategies between LLMs. It was released in July, which is kind of interesting because it's a little not out of date, but it's interesting because we've had so many advancements on and so much more popularity among different collaboration frameworks. So we'll talk a little bit about like what we've seen that's come since the publishing of this paper, which is kind of fun. And then with the paper itself, what it's really trying to do is provide this overview of collaboration strategies for models specifically, and categorizes those kind of collaboration strategies into these three different buckets that you see: merging, ensemble, and cooperation. I'll call out at the start that they are talking about this in the sense of models. They're not talking about this as agents or like I think we've talked a lot about multi-agent kind of approaches recently, but really they're talking about models in this case and how can you get two different models to collaborate with each other. So for those who joined for previous ones, this is slightly different in that sense. So that'll be interesting as we go through. But yeah, so they go through a lot of different techniques that people are using to get models to collaborate with each other in some way, and then they start to categorize these down. So The first one I think they start with here is the idea of merging. So merging different content or different models together in some way. So the way that they talk about these, there's a few different techniques, but the general idea is taking the parameters of one LLM and merging them in some way with the parameters of another LLM that you bring in, or multiple other LLMs that you bring in. So in order to do that, you have to have some kind of combined shared, or not combined, but some compatible parameter space. Like you have to have a generally similar size models. They have to have the same kind of parameter mapping there for you to actually be able to combine them. Because you really are, if you look at the ways that they do this, or some of the ways they talk about doing this, they're done by things like the uniform soup method in this case, which is averaging parameter weights. So you're quite literally like mathematically averaging parameter weights. So they have to be compatible spaces in order to do that. But they talk about the uniform soup method, which is averaging those weights, the greedy soup method, which is kind of take one model, add in the second model, do the averaging there, see if it improves the accuracy of your overall model. If so, keep it. If not, revert it back to a previous state. And then a method called DWA, which is ranking potential candidate merge models on a validation set. And then if they achieve a certain metric there, then bring them into the model that you've created. And so you kind of test before bringing in, as opposed to the greedy soup method of testing after bringing in. And then you can obviously do some kind of weighted averages around how you're connecting the models. So providing a weight for one model as you're adding it in. But they split these into the idea of like merging for relatively optimal solution, so getting the models really good at a certain thing, versus merging for enhanced multitask capability, so adding other kinds of capabilities from models in other ways. And with the former here, the MROS, it's more of combining and averaging weights, versus with the MMTC, it is more combining the models without necessarily averaging the weights, but kind of connecting them in some way with different layers there. So they talk about a few different ways of merging. And if you're interested to kind of go into more detail and more of the mathematics on that, you can jump into the paper and see it. I think it is, we covered the main techniques here, but they go into more detail on what each of those techniques looks like if you're interested in seeing what's happening there. So merging is kind of the first main category that they use. And so then beyond merging, the next piece is this ensemble side. And so ensemble is, instead of combining models themselves into a kind of single unified model and then using that model, it's combining the outputs of multiple models into one result. So it's sort of kind of taking a bunch of different models, having them respond, and then selecting the best result. And they talk about a few different ways of how to do ensemble here. So either ensemble before inference, during inference, or after inference. Um, Before inference and after inference kind of are the easiest to understand here. So we'll start with those two. But before inference is basically using a router. So you have multiple different models. In this case, there are a little like, these are some graphics I stole from the paper. So our little characters here would each be a model. And then when you get a question coming in, you go to have a router send to one of those particular characters or particular models, excuse me, based on how good that model could be at answering the question. So that looks very similar to a lot of agent setups that we've seen, or even multi-agent setups that we've seen. So this is where we start to overlap a little bit with some of those architectures. But yeah, essentially you're using some sort of router in this case. And then I'll skip over to Ensemble after inference, and then we'll come back to the to B here. But Ensemble after inference is basically have every model in your collective group answer whatever kind of question, generate whatever kind of response, and then have some sort of selection process or selection criteria to choose which is the best response there. So basically having all of them do it instead of selecting the best one ahead of time. And then if you look at the middle one here, B, ensemble during inference, is kind of the most interesting, because essentially what's happening here is at every step you are decoding the sort of that step potentially and combining the outputs at that point across the two models as you move through. So you're kind of having them go step by step together, and you're doing some sort of combination at that point. So at each decoding step there, you're connecting the models in some way. And so it's a little hard to tell in the combination here, but you can see basically you have each model take each step and then connect them as they go, basically. So it's an interesting technique. They cite some examples of folks using this ensemble during inference. It's not one that I had seen before, so I think this is an interesting kind of idea. I It's hard to tell from the paper how well this works necessarily. They do go into a little bit of detail here around kind of comparing the extra inference time that these take and kind of the ways that these work. And one call out to make here is that any ensemble method is going to reduce your inference speed because you're using more models to do the same kind of task. Even if you're just doing the ensemble before inference, you're adding that router step. So theoretically, the router step could be code-based. It doesn't have to be a model, or maybe it's a classification model as opposed to an LLM, in which case you're reducing the extra inference time, but in no world are you escaping the extra inference time that's added, even in that before case. And you are kind of gated based on how good your router is at routing to the appropriate model. So you have to either have some training data to tune that router in some way, or you have to rely on a pretty accurate router, which could add more inference time if you're using a larger model in some way. So there's some considerations to make there, whether this is a appropriate kind of technique if you're really trying to reduce inference time by a lot. And then as you move towards the during inference side of things, then you also need to have like you're further increasing the model time because you're basically having each of the three models process the full input. So as opposed to one router and one model in the before inference side of things that's processing it versus in the during inference side of things, you have three models that are processing the input. And you do need to have them have some sort of similar architecture for this to even work because you need to be able to kind of compare these different steps. So the steps have to look somewhat similar in that case, which is kind of, in my opinion, defeats a little bit of the point of the approach because typically you'd want to have different expertise in the different models there. Um, but either way, that is still a possible technique. And then in the inference after stage, this is where you're adding the most inference time, or sorry, ensemble after stage is where you're adding the most inference time because you're having not only every model process the input, but then you're also doing some selection criteria afterwards. So you are basically going to end up with adding an additional selection call in addition to all of the models processing the data. So Ensemble is kind of interesting because it has the most parallels with what we've seen for either multi-agent or agent structures. And it's probably the one that people run into the most. Like if you're sort of thinking about how you would get models to collaborate, Ensemble is sort of the first one that you would land on is like, let's have multiple process things and choose the best, or let's choose the best model to process something and then go from there. So this is the one that we see people overlapping with the most and kind of makes the most sense in a lot of ways towards people who are jumping into the topic. And then the final category that they have is this idea of cooperation. And so cooperation, they kind of treat as the catch-all for other techniques that they would use. And so they even say in the paper it's broad concept, and basically it's using other capabilities of LLMs to accomplish objectives. And then they break down these subcategories of efficient computation, knowledge transferring, compensatory cooperation, and federated cooperation. So we'll talk about what each of those are, but this kind of ends up being the catch-all system, and I think is a little bit more of like a third category here. But the first piece they highlight is the idea of efficient computation. And they talk through a few different things here, but generally the idea of efficient computation is can we use models to reduce the amount of data that we're going to have our eventual model process? So can we prune our prompt? Can we summarize our prompt before we send it into a model? Can we do some sort of like input compression? Basically, can we compress down what we're going to pass into our eventual LLM here so that we reduce the amount of computation that that LLM needs to do by giving it a shorter prompt there? So it means that your input compression layer has to be also pretty computationally efficient to be more to have the overall kind of computation amount here be worth the extra work here. So they talk about these efficient computation methods. I think this is an interesting one because we also see this cropping up not from a efficiency perspective, but if you have a system, potentially like an agent system that has multiple different calls being made to LLMs, it can be very helpful, and we found it to be very helpful to prune and summarize and kind of extract pieces from previous model responses before sending them into the next model. So as opposed to just like continually passing the outputs of one model into the next model as it goes through this sort of sequence of tasks, having some amount of pruning and summarization actually helps from just like I'll say performance, but more performance in the sense of quality of response that you get, as opposed to kind of computational performance. So I think efficient computation makes a lot of sense to do if you're building that kind of system, but it's almost more from a response quality than it is from a computational efficiency process. So that's one of the subcategories they talk through. The next is this concept of knowledge transferring. I'll admit between this one and the next one, I think there's a good bit of overlap, and so I think you guys will see that as we talk through them. But knowledge transferring here, they talk about contrastive decoding. They talk about having basically an LLM review or verify the outputs of another LLM. So using the knowledge in that reviewer to augment the responses from the original model, because that original model is sort of maybe not giving the best response in a sense. So you can have your reviewer model kind of or give you feedback to your original model and have it reconsider certain things. So I think this is another one where it is adding a lot of computation to it. And so I think that at a certain point, the question becomes, why not just use the reviewer model itself? I think in a lot of cases, if you have two equivalently intelligent, strong, powerful models, then having that reviewer step is helpful, but it's almost, we basically just sort of backed into having a reflection step, which is, I think, gives you a lot of the same kind of outputs that you or beneficial performance that you would have here. So there's the knowledge transferring side of things, and then they talk about compensatory cooperation, which is basically the idea of having two models that have the same kind of reward mechanism in place. So they both are trying to push towards a certain collective goal. And so they talk about retriever models in here and having basically like having a RAG system to retrieve information and add it into an existing model. They talk about detectors of responses as well too, which kind of overlaps with the previous one. So I think this gets a little bit used as like what if we just have models that are independent? We're not selecting, they're not doing the same task, so it's not the ensemble kind of thing. There's different models doing different tasks, but those tasks can work together. This compensatory cooperation is sort of basically it forms the catch-all of those approaches. So having these kind of stacked models is going to fall within this compensatory cooperation side of things. And then the last piece here is the idea of federated cooperation, which I think is really cool because I think it's something that I hear a lot of times talked about within the context of AI on mobile devices and on these sort of smaller computation engines, where you have essentially a larger server LLM, and then you have more maybe smaller, so SLMs within a client here. And there's a couple benefits that come from this. One is sort of the obvious, like you can have your client only have to maintain and hold an SLM. So if you're thinking of things like mobile devices, they may not have the memory to run a full LLM, so you can run an SLM on that device. And then if that client needs the extra intelligence or computing power or whatever it might be of the LLM, it makes a call out to them. But the other benefit that comes from this is the kind of security aspect. And so you can see the kind of the locks in here giving it away a little bit. But the security aspect is nice because you can basically have any kind of specific, call it PII, call it other information, retained in the client SLM, and then have that get obfuscated before it goes to the server LLM. So in a lot of cases, you can retain any personal information on, say, on the mobile device before it's actually going to the server, and then it's going to get processed there. So you can kind of get the power of the LLM while still having the privacy of maintaining a model on device and all the data on device. Obviously, you're adding a latency for the extra call that gets made. You have to have network connectivity between the two things. So not going to work in every kind of capacity, but the idea of this like federated cooperation is kind of an interesting one. And I think something that we'll see more over time with mobile devices and things like Apple Intelligence and these other kind of tools coming through here. All right. And that is all the categories that they go through. So I think I have a couple kind of final thoughts that we'll talk through for a minute or two here. One is that they're in a way, this is kind of like adding another set of categories to something where we have some existing categories. So I think there are very useful thoughts, I think, in the paper here, but I think it goes a little overboard on categorizing everything. You guys may disagree. If you do, please drop it in the chat. But I think it's interesting to see them kind of try to fit everything to categories. One sec, I just see something in the chat. Yeah. So there's a question around, this is interesting from a research perspective, but do you have any demand for this research in real applications? Like this would get, yeah, you get laughed out of a boardroom if you told folks you were going to have to run 3x inference time and cost by having multiple LLMs cooperate for a RAG application. I think in a way, there are some pieces of this that do work and are worth it in a real world setting. But I think this is where almost the idea of having these extra categories is a little funny because we've kind of reinvented existing concepts with these categories. So for multiple, like in the RAG application case, for example, you wouldn't necessarily have multiple LLMs collaborating for the RAG side of things. I think if you think of a typical RAG system, like you are going to have, you would actually, I guess in this case, they would have an extra LLM collaborating there. So I think in this particular one, you wouldn't necessarily see that system. I think the federated piece is one where you might see it. And then I do think some of the ensemble um, pieces would come through. Like we do see this sort of approach used in real world settings. I think frankly, we see the ensemble before inference used a lot of times because I think where this would be applicable is say you wanted to have a router, but you were able to reduce all of these models to SLMs and just have them be more specialized for certain tasks, you could actually reduce your overall cost. I think your latency might be similar because I think that while SLMs are going to be faster, like the difference isn't big enough that you can completely offset the addition of a router step. So I think that you'd have similar kind of inference speed, but you'd have cheaper costs, and you might be able to have the same level of performance if you had a good router and kind of good coverage across the SLMs. So we do see that kind of a flow in a real world application. I haven't necessarily seen the ensemble after inference being used in real cases because I think that you could do them in some kind of specific one-offs, but it'd be hard to find a real kind of enterprise use case that's going to be made better in that situation. Um, and then for these pieces, I think similarly, the one that I would call out that is useful is having some form of reflection step. Like if you're going to build a multi-step agent, having something like this, either knowledge transferring or compensatory cooperation of basically not augmenting a RAG system, but having a reflection step that's done by either the same LLM or another LLM. I think that can drastically improve the response that you're going to have from an agent. So I think that could be useful as well to not 3x the cost, maybe use a smaller model for the for some piece of that or something like that. But I do think that you could be 2xing the cost by adding the reflection step. But it could also be the difference of strong versus weak responses from your system. But great question there. Yeah, yeah, you're right. Ensemble performance is just a mixture of experts. So that is a good call out there. Um, but yeah, I think that's kind of the bulk. I guess the last point I had here was just how this relates to agents and multi-agent systems. We kind of talked about this a little bit, but I think it's always kind of fun to mention this is that we're talking about models collaborating, but in a lot of case situations, multi-agent systems are models collaborating that are just with some extra steps that have been added in, specific prompts or things like that for those certain models. So I do think a lot of these systems, while they're specific to models, the same thought process can be applied for some multi-agent systems as well too. So if you are deep in the multi-agent space or you're thinking about collaboration strategies or anything like that, then I think it's worth diving a little bit more into some of the strategies in the paper because I think they do map over to what we see within agent systems, not entirely, but somewhat there. And awesome. And we're right at our time, so perfect timing. We'll stick around for another minute or two if anyone has questions. But otherwise, thank you guys very much. For anyone who's in the Bay Area tonight, we've got an event tonight at the GitHub offices. So if you are in the Bay Area and you're interested in joining for that, then we can check out our events page. We'll have more details on that there. And otherwise, I think we'll have a few more of these before the holidays. So I won't say happy holidays yet, but thank you everybody for all the attention here.